All right, sorry about that. I have to make it in two different videos here. So you have the change in population over the change in time as birth minus deaths. All right, so then births and deaths can be expressed as the average number of births and deaths per individual given the specified time interval. So what that means, all right, we're going to say B, which is, remember, is the number of births, is little b, big N. All right, where little b is the annual per capita birth rate. And then D is little m, big M. So M stands for mortality, is the per capita death rate. And N is the population size. So let me give you an example of the birth rate. B is the annual per capita birth rate. So let's say we have the statistics. There's 34 births per year in a population of 1,000 individuals. So the per capita birth rate, or little b, so little b would be the number of births, all right, divided by the population size. So 34 divided by 1,000. And so when we divide that out, we'd end up with 0.034, and that is the birth rate. All right, and so then you could do the same thing for the deaths. To get M, it would be the number of deaths per year divided by the number of individuals in the population, and that would be your death rate. All right, so you have your birth rate and your death rate. So if you know for a population, the per capita birth rate, all right, then you can apply that to a population of any size. And so an example to piggyback on that is then if B is 0.034, or 0.034, the little b, big N, and your population size is, let's say, 500, then you multiply this out, and big B is an increase in 17 individuals per year. All right, with a population of 500. If the population was 700, you'd multiply it by the same little b, which is the per capita birth rate. So you figure out the per capita birth rate, and then you multiply it by N. And you do the same thing with D. Okay, so that's an example of that. Now it says the population growth equation now can be revised because we've redefined what B and D was. So we had the change in the population size over a given time period is B minus D. Well, now we can substitute in for B. Instead of B, we write little b, big N, minus little m, big N. All right, so that's the number of births. So what you get when you, that's like what we did here, the individuals that are increased per year, and minus the individuals that the population are going to be missing that year, the deaths. And so you do the same thing with the death rate, and you end up with the change in population. So either there's going to be more, this is going to be higher than this, and you're going to have an increase in the population, or this is going to be lower than this, and you're going to have a decrease in the population. So then it says the per capita rate of increase is given by, so the rate of increase is R, so R equals B minus M. It's the birth rate minus the death rate. So let's go back up here and do that with the death rate. Death is MN. So let's say the per capita death rate was 0.016, all right, and the population, and the population was, again, 500. You multiply that out, and then you would get 8 deaths per year. Okay, so really we would have 17 minus 8, and that'll give you an increase. Or what this is saying here is the rate of increase is whatever the birth rate was. So I'm going to get this in. So B minus N right here is whatever B was, which is 0.034, minus whatever M was, and I didn't calculate M for us, but if I did the same thing as up here, M would be 16 deaths per year in a population of 1,000, would give me 0.016, and so then if I took my birth rate minus my death rate, so we plug in, I haven't done this yet, so 0.034 minus 0.016 gives you an increase of 0.018. And so let's write that as an example here. So the example using this data here is 0.034 minus 0.016. And so therefore, we'd get an increase. So the rate, R, would be 0.018.
Terry Spencer.
So you guys, I think I forgot to hit play here. Zero population growth occurs when the birth rate equals the death rate. So if this 0.034 equaled this and this was 0.034, if the birth and the death rate are the same, your rate of increase is going to be 0, and your population is going to stay the same at 500. So now that we know that what the rate of increase is, we can change our equation about the change in population over time to Rn, where R is that rate of increase and N is your population size. So if I took the 0.018, that was my rate of increase, and it's a positive number because the birth rate was higher than the death rate. It was 0.018. My population size was 500, so my change in population over time was 9 per year, and that would be the same as if I took the B minus D, 17 minus 8. And so therefore, our equation has changed. Change in time, or change in population over change in time is Rn. So then it says instantaneous growth rate can be expressed as, and it says R instantaneous, where the R instantaneous is the per capita rate of increase. And we're just going to look at this Rn here. So let's apply this here, and I'll tell you exactly what you need to know about exponential growth. So exponential population growth is population increasing under idealized conditions. So if there's enough resources, space, and so on. Under these conditions, then, the rate of increase is at its maximum, denoted as R max. And this is important. The rate of R instantaneous for the AP test, they want you to know R max. So R max, the maximum rate of increase. That means if everything's ideal, it's the fastest rate at which those organisms can reproduce and increase. And the fewer the deaths and the more births. The equation of exponential population growth is therefore, and they take, it says dn dt. If you've taken calculus, this makes a little bit more sense to you. If you haven't, we're just going to think of it as the change in population over the change in time, like we have up here, and so on. And so what you need to know is it's R max multiplied by the population size. So these are under idealized conditions. They're going to grow at the maximum rate, and to figure out by how much it grows, you'll take the population size and multiply it by that max. And so this you need to know for the AP test. All right, what R max is. So exponential growth results in what we call a J-shaped curve. So if we look at the next page here, it explains the J-shaped curve. So if we look here, it looks like the letter J. So that's where it comes from. All right, the rate of increase, though, is constant. But the population accumulates more new individuals per unit time when it's large than when it is small. So remember, this is the equation is change in population size over time is R max N. So therefore, the rate stays the same. So R max stays the same, but as N gets bigger, like N being 2, you're going to increase in a smaller increments than when N is 100 and you multiply that, then it increases at a greater, increases more individuals per time period. And so that's why it starts out slow and the population's slow, because it doesn't increase by very many individuals, even though that rate is still the same. And then as time goes by and the population gets bigger, then and N gets bigger, then it increases every year or so on by way more individuals. And so so when you see that the rate is 1, you get a steeper curve than when the rate is 0.5. All right, even with the same population size, even with N being N at the beginning being the same. And so, but as N increases, in each case, the rate stays the same. So in this, I guess I should say, this particular graph, the rate stays the same and N increases. From here to here, if you change the rate and the rate changes from one population to another, it's still a J-shaped curve, but a population growing at a slower rate of increase, the R max, is going to take longer for it to show that J-shaped curve, but it eventually will. And so then if you had 0.25, it would be over here. And so the rate does change the curve, but when you look at one individual with one rate, and the rate doesn't change, the size changes, and so therefore it goes up many more individuals per time period. So the J-shaped curve of exponential growth characterizes some rebounding populations. So example, the elephant population in Kruger National Park, South Africa grew exponentially after hunting was banned. So they were almost hunted to extinction, and then they banned the hunting and kind of preserved them in this national park. And they began, you can see here, this is the growth, they began growing exponentially there. All right, so what they found eventually, though, is that they began using up, the population became so large in this park that they began to diminish the resources and so on, and kind of destroying the habitat there, and they were concerned about starvation, and so they actually implemented and began limiting population size in the elephants. But they actually implemented birth control, and they actually exported some elephants to other countries as well. But that's an example of exponential growth where the population is rebounding from a catastrophe such as humans hunting them. And so that is exponential growth. So now we're going to switch gears and talk about, realistically, populations don't grow exponentially forever. So you just said about the elephants, and realistically they're not going to be able to grow forever because of their limited resources. So the logistic model describes how populations more realistically grow slower as it nears what we call the carrying capacity. So exponential growth cannot be sustained for long in any population. A more realistic population model limits growth by incorporating carrying capacity. So carrying capacity is represented by the letter K. The maximum population size the environment can support. So it varies with the abundance of limiting resources. So the logistic growth model. In the logistic population model, per capita rate of increase declines as carrying capacity is reached. So per capita rate of increase was R. So remember, it's the birth rate minus the death rate. So it begins to become closer to 0 where there's not growth. So the logistic model starts with the exponential model. So remember, the exponential model was this, the change in the population size over time is R max n. So it starts with the exponential model and adds an expression that reduces per capita rate of increase as n approaches k. So as the population size starts reaching that carrying capacity, what's going to happen is we need to reduce that r. And so we add a section into this where, so r max multiplied by n, and now we add in, we multiply it by k minus n over k. So let's explain this. So K is the carrying capacity. So we're multiplying, so the maximum growth, this is the maximum growth rate, but as the population gets bigger, this our max and the growth rate should go down because as it approaches carrying capacity, let me show you this graph on the other side here. So this was exponential growth. As it approaches carrying capacity, I drew this on the board the other day, this dotted line is the carrying capacity, so the nearer it gets to carrying capacity, it starts to level off. This is called an S-shaped curve. So we're talking about here that rate of increase is going to get slower and slower until eventually it may be at zero or fluctuate really close to zero as those resources diminish. And so let's look at why this part of the equation does that to the exponential part of the equation. So if the carrying capacity, let's say the carrying capacity is 1,000. So if we took 1,000 and let's say the population is only 10, 1,000 minus 10, what's that, 900? 900 divided by 1,000 is going to be what? 0.9, right? It's really close to 1. And so when the population n is really small and you multiply this, it's really close, multiply it compared to the exponential model, it's going to be still really, really high. But let's look at what happens when n gets bigger. If n is 999, all right, so the population is getting closer to that carrying capacity, then your number is going to get closer to zero. So if the carrying capacity is 1,000 minus 999, that's 1, divided by your carrying capacity, which is 1,000, that is 0.001. It's a very small number. And so, and imagine when it reaches carrying capacity, you end up with it being 0. So 1,000 minus 1,000 is going to give you 0. And so then notice here our rate of increase goes to 0 because 0 times anything gives you 0 growth. So therefore we're going to have the bigger n, is, the closer to 0 it is, the less impact, or the less growth, I should say, the population is going to have. So when n is small compared to k, when n is small compared to k, see if you can answer the next 3 here. Pause it. When n is small compared to k, the term k minus n divided by k is close to 1. All right, so that was the example, like of the example of 10 that I talked about. And the per capita rate of increase approaches the maximum. So it's close to the maximum. So you're going to still grow at a high rate. When n is large and is really close to the carrying capacity, then k minus n divided by k is close to 0, and the per capita rate of increase is small. When n equals k, the population stops growing, and that's because this number is 0, and so therefore you have no rate of increase. You're at the carrying capacity. So here is a hypothetical population where the carrying capacity is 1,500. And so what you see here is, this is the R is 1. So we keep that the same, that's held constant, but the population size gets higher over time. So k minus n divided by k, all right, so 1,500. So if you took this, I'm just going to get my calculator out here so you can see. All right, so we would take K is 1,500 minus N. So N is not very big yet. So what would we expect? We're going to expect it to be able to grow at a high rate because it's not close at all. 25 is not close at all to the carrying capacity. All right, so 1,500 minus 25, and then it says, and then we divide it by the carrying capacity, which was 1,500, and see, you get 0.98. So that then they're using the same equation. So we just did this part of the equation. Then you multiply it by R, and it tells you that R is 1. So that's the same. So that's why these guys are the same. And then you take that and multiply it by N. So this is so 0.98 multiplied by N. N was the population size. So we multiply it by 25, and you get, rounding up, a positive 25. And the positive is telling you that you're increasing the population. All right, and so then you do the same, then it grows to 100 and so on and so forth. And you can see that when it gets to 1,500, when we do this K minus N, K is 1,500 minus the population size is 1,500. All right, so you get 0, and so therefore the growth rate is going to be 0. All right, and so that's how that works. So the logistic model of population growth produces a sigmoid or S-shaped curve. New individuals are added to the population most rapidly at the intermediate population sizes. So in that middle part, population growth rate decreases. In exponential growth, the growth rate stays the same, and you get that J-shaped curve. But in logistic growth rate, it decreases as N approaches K, as the population size approaches the carrying capacity. So if you look at the other side, we already looked at this picture, but let's look at it again. And so here's your exponential growth, where you get the rate R max is 1, and so that's the equation for exponential growth, and you get that J-shaped curve. So now we have a carrying capacity. So here is the R, this is R max, here is 1, Rn, and K minus N divided by K. And so that's what they're showing you here, where they're just plugging in. R is the same exponentially here, but this doesn't grow continually exponentially because it approaches the carrying capacity, and so the carrying capacity is 1,500. So as N gets closer to that 1,500, it gets closer to 0, and a 0 growth rate is a flat line and has no slope on the curve. Okay? So let's look at here a couple of realistic populations. The growth of laboratory populations of Paramecia. That's plural for Paramecium. Fits an S-shaped curve. These organisms are grown in a constant environment lacking predators and competitors, and so therefore they have enough food and all of that kind of stuff to be able to survive, and there's nothing going to kill them. And so here's the Paramecium, and we see that until eventually, so they're growing eventually where nothing's going to kill them, and then they reach that carrying capacity, and that carrying capacity seems to be close to about 900 or so, 850 around there. This is Daphnia, sometimes they call it a water flea. They live in fresh water as well. Both of them live in fresh water. This also shows an S-shaped curve. Notice here they did the curve here, but notice this part here. This is called an overshoot. Sometimes the population can be growing exponentially for a while, and then they have too many kids, and the population gets too big, and then we're like, oh, we don't have enough space and resources, and some of those die off, and the population begins to level around that carrying capacity again. So sometimes that's an overshoot. So some populations overshoot the carrying capacity before settling and around that carrying capacity. And this is where I'll stop in the notes. So there are two parts to this.